Welcome to another Plan 6 parts video. Today's video, tr6 engine cylinder bore measuring theory. Yeah, that's a long one. Anyway, this is not one of the normal videos I do. This one is something to throw out there to the Triumph community on, basically I'm looking for opinions. So basically, normally we measure the cylinders the same sort of way to see if it's out of shape and so on and so forth. However, what I was doing now, I have an engine here that's been bugging me because it's at the crisp of being out of size. What doesn't help is that it was also stamped F and not AB. So it's bugging me because it's pretty much out of size, but at the same time is that I'm thinking, is or isn't it? It's just, I'm trying to get the exact number because obviously you don't want to machine if it doesn't need it. But don't get me wrong, it's always nice to machine it anyway, but it's a cost thing, let's face it. Anyway, follow me with this and see what you think. And again, this is something to throw out there for opinions and opinions only to see what people think. There's not a dig about anybody or saying anybody's doing it right or wrong or anything like that. Just make that perfectly clear. So let's go through the process. So I've done my calculations here, and I've actually done it in mil because I have both a mil and a metric gauge. That's how it's been wrecking my brain so much. I've been doing it in both. I've done it in metric and I've done it in mil, just to see would it end up being the same. And it could be a little controversy to say. Anyway, let's look at what happens. Okay. So usually what we do, and let me zoom in a bit. We take our measurements off a set number. So 2.940. Well, it's actually 0.5. All right. And that is a grade A bore. Now that's the smallest bore. That's where it starts from. And usually when we do a number, so what we'll do is, up here, this is a mil though. When we work out, we start with that, we set our dial gauge to that, and then anything, should I say, on the dial gauge, less on the dial gauge, which means it's bigger in size, we write that down as discrepancies. When we get discrepancies, we see basically the taper and so on, where our measurements are, right? I'm not going into all that. And then we find out, we add it all together, take the biggest size, and we basically get a cylinder size, right? Then we go back to this and then compare to see if it's out of size. I mean, do we still have an apple or do we have a lemon? Anyway, what we normally do is take that 0.1 mil, right? Now, again, there's nothing in the book that says that. So, like, first of all, I'd like to know, even though we use this, who started this? Who started at 0.1 millimeter? It's unofficial in that way because it's not in the book. No, I'm saying it's not in the book. I guarantee it is in the book. We just can't see it. Maybe it's in there but not clearly written. And maybe it's just a case of that when you get to a certain point, like if you think of it like your bearings, when you measure the journals and it gets to a certain point, you go up a journal. Or you go up a bearing, but yet you don't machine the journal. Do you know what I mean? The gap has gotten bigger, you don't machine it, but yet you fill in the gap with a bigger bearing. So why are we not doing the same here? And this is where my train of thought is going. So they say 0.1 mil is the tolerance, right? So based on inches was 0.003 and I think it was 8, right? But you could say 0.003 to be safe. And you end up with 2.344. Yeah. 8, 9, 10, 5. Oh, sorry, 3. So you end up with 2.9443. All right. Now, that's usually the number. So if you say based on 2.940 as your starting point, you'd end up with 4 tau. Almost 4.5 tau discrepancy to know it's out of range, right? Makes sense? Yeah, seems pretty straightforward. You could do the same for millimeter. So your millimeter is 74.70, and you add your 0.10 on, and you end up with 74.80. All right. Sorry, the pencil's not sharp, so it's not great. And then you do the same. So you basically, anything within 0.10 mil, that was terrible looking. As long as you're within the 0.1, that's fine. So basically you have 10 thousandths of a millimeter, or 10 hundredths. Not sure. Anyway, that's what you're looking at. Now, here's where it started to change for me. Is that, I'm going to show you the book. Sorry, this pencil's driving me nuts because I need to sharpen it now. I don't have a sharpener here. Here's the book. Now, follow me with this one. We're taking a number off this, 2.9405, right? Or 2.940, just to be sure. And that's the grade A bore piston, the bore size of the piston. If we take our engine, and we take our cylinder, we take our pistons out, and we measure this, and we go through all this process, and it's all within range, that's fine. Everything is going hunky-dory, doesn't need machined. So what do? We can either clean these up if they're right dimension and these are not worn, which theoretically, if this is within range, then that should be in range because one has to match the other, theoretically. So if these are still haven't been worn down, you expect them to be, correct. However, what we can do is do this. We go out and buy brand new piston. So this is a brand new piston head. As you can see, it's for a standard size, 74.70 mil standard size. All right, still straightforward? Yeah, okay. Let's move on. Your engine has some grade B ones in there. As you can see, the difference is basically half a tau. So you have half a tau different size for the A, and you have a half a tau different size for the B. The difference between the two is 1/1000th of an inch. So you take your B out, you measure it. But you measure it from what? Do you measure it from this number? Or are you measuring it from the A number? That's the question. If that was the case, you should be measuring it from this number for the B's to see if it's within tolerance. Let's say you did. Let's say you took this number instead, 2.941 and not 2.940. And you measured it and you've done the same thing, calculations, and it was within tolerance. So you've done all your numbers, everything matched up. That's fine. You know what? I'll put new pistons in. What do you get? Hey, look, this looks the same. It's the same standard 74.7 mils piston for that. Same piston. Because they're different sizes, and this is what can confuse you, is that if you're using this number for grade B, how do you know this is out of range? Because you're starting off 1/1000th of an inch smaller already, theoretically. When I say theoretically, is that, look at the numbers. This one, you have half a tau between sizes to make sure that this is how it's bored. Straight, no discrepancies, no oval shape, no nothing. This is how it's machined, so it should be perfectly cylindrical. Oh, thank God I said that word. Between this and this. The same applies for this, between this one and this one. So perfectly cylindrical. So when you're looking for tolerance, or you're looking for wear and tear beyond the norm, what number do you go by? Do you go by the first number or the last number? And this is where I'm going with, is that we normally go by the first number. That's the smallest size. The largest size available for the B is pretty much 1 tau bigger, but yet there's no discrepancies in there. So why are we adding discrepancies onto this number? For me, this is where I'm thinking, is that the cylinders, no matter which one you pick, they're still within range. So if you were to do your, let's say, your A's, and one of them was larger and out of range, you'd probably bore it. But yeah, for the B, the same cylinder, for the same piston you will put in it, if it's a standard, if you know what I'm saying, it's not. So this could be out of range, but still be in range with this. And if it was in range with this, you wouldn't machine it. You'd put a standard piston in. So my train of thought is this, is that, why are we using this number? By right, we should be using this number to start with, a 2.9416. Basically 1 tau more. That should be our starting number. Because we're using the same piston for both sizes now. You can't get an A and a B. Or can you get an F, a G, or a H? You use the same. So the same rule, I think, should apply for the millimeters. So let me go back again. Same for the millimeters. If you look at it, if you want to do yours in mil, instead of starting off at 74.68 or 74.70, which I'd probably go 74.70 based on the thing. But if you look at it, it's designed for that. It's not giving you the lower number, it's giving you the larger the numbers. But again, if you had this piston, the grade B, it doesn't say 74.71 on that piston. It says 74.70. So that's what I'm getting at, is that how on earth can we measure the grade Bs and still put them in the same categories as the A when there's nearly a tau difference? That's what I'm getting at, and that tau difference is a difference of whether it gets bored or not. So to me, and I'm starting to go this way, is that instead of using the 2.94, I'm going to start using the 2.9416 or the 2.941.5, if you want to call it that. Because I can get a 5 on the gauge, I can't get a 6. Because I use the digital one. And I'm going to start with that one number. Because that's the largest number available with no discrepancies and no wear and tear. Wear and tear, if you have something this size, it starts here and ends here. The wear and tear goes from the end point, not the beginning. That's the beginning. That's the smallest. You're adding in wear and tear into this. That's 1 tau mil, or 1 tau of an inch. Your wear and tear that doesn't exist. Yet you're adding it in there. And we've all done that. And I have done that. And that's where I'm going with this, is it possible that we're now wrong? Let me show you something else, right? So, I've got a piece of paper to do this. Over here. So let's say we start off, right? We start off with our 2.940. Then we add on our 0.003 thousandth of an inch. No, because if you're not adding that 5, you're not adding that 8. Simple as that, would you say? Otherwise you would. Because the difference is you end up with 2.943. Well, in this case, if you added on your 5 and you added on your 8, let's say, for the calculation of it, you'd end up with 944.3. So you've gone from 43 to 44, almost 44 and a half. That's like, you could literally, to come up that, you're literally adding half, in reality, you're adding half a tau onto this, right? So the maximum, if that you want to call it, is 45. So that gives you basically 5 thousandths of an inch. 5 thousandths of an inch. Using that way. Now, that's only going by this 0.1 mil discrepancy. Since it's not in the book, and I said I've looked through the book and I can't find it. Now, when I say I can't find it, I haven't read this thing like a book. I'm terrible for taking information out of books in that way. If somebody actually read it, I guarantee. But who came up with this number? Who? It's not in the book, so somebody had to assemble. Is it in a different book? Is it in a Haynes book? Is it in a different manual? Like, where did this come from? This is why, because I want to go into something else and you may explain this. Let's say even we did use this number, that's fine. In mil, you do the same. You do your 74.70, which is based on the piston. I'm going by this number, because that's what it's designed for. And then you add on your 0.10, and you end up with 74.80. Seems pretty straightforward. So anything beyond your 0.10 is out of sync. So there's your out of sync, and in this case your out of sync is this number. It's actually, well, it's 43, but you could say half 5 thousandths of an inch, because you've gone from 0.0 to 0.5. So I'd say half a tau. 5 thousandths of an inch, so 0.005. Would anyone agree on me on that? Maybe. Like I said, that's going up a small piece. In reality, it would probably be 0.004. So 4 thousandths of an inch. Anyway, so you can see where this is the numbers, how it goes. Now, what if though, right? So once you go beyond that tolerance, right? Once you go beyond this tolerance, or go beyond this tolerance, it needs to get machined. And you need to go up by 0.020. So 20 tau you need to go up by. My question is, why is it 20 tau? Why not 10? Yes, you can't get, there's no 10,000 pistons or rings out there. Why? Why is there not? And this is where we have to think about it. Like, and somebody else has said this, and it never dawned on me when I thought about that. Why is there no 10,000s? Why everything else, like the bears and everything, start like tr6 at 10. So why did these not? Why did these start at 20? Why do you have to go up 20? So I know if you reboard it, you base it off the 2.940, and you'd end up with 960. Sorry, the pencil's terrible. 2.960. But again, that's your starting number. So where's the end number? Is the end number, like if that was the case, where's your tolerance in here? Where do you get your number before tolerance? Is it 2.96? It should be 2.9605. That's what it would be. Is it 2.9610? Is that what the new number you're going for all the pistons? Because that's based on the standard size, which theoretically would be correct. Yeah. So again, agree me if you're not. Based on boring it, that's where you start, and then they'd all end up the same. There you go. And then you take, to me, if you'd done that, you'd add a tolerance onto this number, because that's the larger the number that's acceptable without any discrepancies. However, based on the machine you already have, it includes the grade B. And the grade B goes all the way up to 2.9416. So right now your engine can go this high, this wide, without it having any wear and tear. That's how it was machined. So if you add on to that your 0.003, let's say you're 0.038, you now end up with a number 45492. You end up with 2.9454. So it's almost reverse of this one. So now you have pretty much 5.5, your 0.0055 discrepancy. And the reason why this number is a little important is that I know one of Ellen's videos, on one of his videos, he was doing the machine, and it's offhand, I'm trying to think of that, he ended up at like 44. And he's like, oh no, that's out of range, so it has to get machined. But according to the numbers, if you use it for both A and B, now again, someone might say, well, okay, there was no B's in it, it was all A's. That's fine, absolutely fine. But what happens if there's only one B? Once there's one B in it, then you have to use this number, because you're going to treat them all the same with the same. This one's going to go into the same one if they're all in range. So you're either going to calculate the B wrong, or you're going to, like, you're treating them all the same. You're either calculating this wrong, or they all have to be calculated from that, because the same piston's going into them all. Does that make any sense? Sorry, it was blurry there. So that's where I'm going with this. Now, you do the same with millimeters. So in reality, this should be your number. It keeps going out right. It will focus, I don't know why. The same for the millimeter. 74.17. Yeah, I might have to zoom in a bit more so you can see it. 74.17. You add on your 0.10, and now you have 74.27. That should be your size. And when I done mine, so sorry, 74. Sorry, I wrote the wrong number. My mistake. Huh? I was wondering there for a second. Let me do that again. The millimeters is 74.717. Now I don't know about you, but I can't get that 7 on. If I do millimeters on the gauge, the dial gauge, I can't get that one. or the micrometer, the electronic one. I can't get that. Now you'd probably be able to get that on a on one of these styles. Hang on, hold on. I use this one. Sorry, it's really close. That's how I use this. I use this one and I put it in inches because I get more numbers and I get a bit more closer. Otherwise, I lose the last number. I'm pretty sure if you had a millimeter one of these gauges, so you'd be able to get it no problem. I'm still trying to figure out how to get these fine-tuned. I'm not going to lie. I'm still trying to work that, especially for measurements. Like, it's one thing moving it to measure in, but I find it hard to go measure out. So, yeah, not gonna lie now, I'm still figuring that one out. That's why I like the electronic. Anyway, so we're gonna go with 74.771, let's say. Let's take that out, and we add on our 0.10. Then we end up with 74.81. Now, if I didn't do that, I end up with 74.80. So that's 0.01 millimeters. Yeah. There should be well, no, you have a 0.1 discrepancy. Sorry. So if you have 74.7 and you have 74.71, yeah, it's an extra 1 mil. So here's the thing: is that when I was doing it, you 74.8. When I was doing mine, I ended up with 74.79. Look at this one, 79.79. So this is 6.54. These are the ones, these two, this was the one that was terrible, this one. But this one is just as bad. And obviously you come down a bit, you have 6. So they're not the worst difference in the way of to themselves, but obviously 4 and 5 on pretty much every engine, tr6 engine, takes the brunt on everything. It's always 4 that's fouling. Always that one. I don't know why. Just seems to be. But yeah, so based on that number, and I use my numbers here, I'm within range. I don't have to machine it. But yeah, if I went and when I used this number, and I've done it in inches, I was out of range. So that's the difference, is that theoretically, I'm going to go by the later numbers because tolerance happens after. And the other one is that, here's the other one I was getting at, is I was talking about, and sorry if I'm rambling on here a bit, I was talking about the difference of why you have to go 20 tel. Why do you have to do that? Why not 10? Here's my theory, and again, the theory is that there has to be a point where 10 tel is in here somewhere. So my theory, and this is a theory on this, is that like a bearing, the tolerance level is based on your bearing size. If you think of a bearing, if you go and you're, let's say, 10 tel out or 8 tel out, you'd go up to a 10 and oversized, if you know what I mean. Like once you reach beyond the limit of a bearing, you go the next size up. That seems pretty plausible. That's what we do. We measure to see how big the gap is, and we fill the gap. With this is, where do we put that 10 tel? Do we add it to here? So theoretically, we go from 2.940, and do we add the 10 tel, so it's a 2.950? Is that where we're going with this? Because when I done this one, it was 4.5, and it's like 5 tel, well, 5.5 actually. It's even bigger again. Or do you add 10 tel onto the later number? So you're 29416. So 29416 plus your 10. And you end up with 6159. So would you think this number here is your tolerance? Because you know you've gone 10 tel, and after that, theoretically, should be 20. You've gone beyond the 10, so you have to machine it. So I mean, it's, I don't know. Like it's that whole, at what point do we go to 20? Like, and the only reason I say 10, and I'm probably saying, well, where are you getting this 10 tel from? There's no 10 tel. I can't get these plus 10. That's right. The reason why is that if my brain is thinking like a bearing. So when you get to a certain point, you go to the next size up. When you get to that point, you go to the next size up. There has to be a point where you go from 10 to 20. That's why you're machining at 20. Why not machine at 10? Why is 10 not available? So there has to be 10 tau somewhere in these numbers. That's the only thing, logical thing I can think of, is that there's a 10,000 discrepancy somewhere. So that's why you go up by 20. And then from there, because you've gone up and you've remachined it, and then it goes up in intervals of 10 again, because you've already reset them all. And the reason why I say this is because you're looking at two different sizes. You're looking at an A and a B, not just one size. If it was one size, I wouldn't bother trying to figure out why the 10 tau is not in there. I'm thinking the 10 tau is a difference between the smallest point of the A, the largest point of the B, plus any wear and tear. So, I don't know. Maybe I'm completely wrong with this. Maybe I'm stirring the pot. I hope you get where I'm thinking with this, is that, like, where did these numbers go? Like I said, like, this is an unofficial number, that 1 mil. Who came up with it? Like, where did it start from? Was it somebody who worked in the shop and says, well, they don't do it this way? Well, that's their tolerance, compared to a modern car now, which is they give you a tolerance number, but in reality it's a lot bigger. That's their safe number. So, like, it'd be nice to have something defined in a way, something that's written, that if you go beyond this tolerance, that it's no good. So, and I suppose maybe some people say, hey, that's enough, like, engineers who say that's enough tolerance, that's beyond there, you're not getting the same efficiency, so it's best in machine or whatever, for any engine, which is fine. I credit that. I get that. I mean, you want a nice running, the best engine you can get, especially if you're throwing money at it. So I get that point. But it'd be nice to know where, because look at all these numbers, like, where are we in this whole jib-jab of numbers? Like, what's defiance? I'm willing to think, like I said, like that. I said, if you add a 10 tau difference, you can go beyond it, because each of the rest of them go in 10 tau, like from 20 to 30 to 40, 50, 60. So, like, there has to be 10 somewhere in here, and I think that's adding on. So you're basically giving 5 tau difference between A and a 5 tau B, and you end up with 10. Oh no, maybe I'm getting completely lost in my own head here with numbers. But for me, I'm going to go, and if I stick with that 1 millimeter, I'll add it to the largest of the millimeters, and I'll end up with 74.81. So according to me, when I done mine, these are all within range. But if I'd done it based on the first one, they wouldn't be. So that's my train of thought. So it says, let me know what you think. And it says, there it is there. Oversized starts at 20 tau. I mean, you have to machine it to that. And I get using this number, because the next size up, it should be written on the box what size it is, and that's fine, I get that. But for this, in this sense of measuring our D's in range, we have to bear in mind there's grade B's in there. And what if you don't know there's a grade B? How would you know? You could turn around and get your piston, and let me show you on this one, hopefully it is there. This, as you can see, is stamped F. It's really early. Right, so you could have a G or a H as a B. But what if your piston could be stamped with, let's say, an A, for argument's sake. But the actual block itself, and if you've seen my other videos that I can show you on this one, is that the early models have each stamp. I don't know if you can see this. Hopefully you can see it. You can just barely make out an F. Hang on, I'll see if one of these are more clearer. Maybe this one. You can see, oh, where's the cylinder? Can you see the F here? I don't know if you can see it. This one seems to be the clearest, I think. Where is it? Right here, see the F? There it is there. That's stamped F. And with the early models, that's stamped all the way down it. So you would have A, maybe a B, A. The later models have 3 here and 3 here. So if you don't see that, how do you know what you're measuring? And that's the thing. This is the whole idea of, like I've done before, is eliminating the possibility of discrepancies. How do you know which cylinder it actually was? Was it an A or a B? Just because the piston says A, that doesn't mean that somebody put an A back in at some point over the 50 years and didn't know. So you're measuring an A when it's really a B. So I mean, so if we don't know what size it is, for sure, and whether it's an A or B and it's within range and we replace them with new ones of this, I'm telling you now, that's where I'm going, is I think we have to use the last number. And the 2.9416 or the 74.71 mil. That's where I'm going with this. So again, I'm going to throw it out there. Let me know what you think. Let me know your thoughts on it. Again, this is not a big grudge match to say this is, oh yeah, this is right. No, everybody's wrong and all that. That's not that at all. I just want to see if anybody agrees with me where I'm going with this. Maybe somebody already else does it. Maybe somebody doesn't. Does it have any weight to it? But you can see the logic where I'm getting at. And I hope you see it that way. And again, it's your choice. If you want to measure it using this and it goes out and you want to bore it, by all means. It's not that at all. It's just a case of trying to find the right way. Like maybe there's machines or maybe there's blocks that are being bored when you don't have to be. And again, nothing's getting cheap nowadays. So maybe there's the possibility that it's just cutting that cost down. Maybe we're skipping something. I don't know. It's a choice. Like I said, if I had the money, I'd machine them all anyway, just for the sake of having that better compression and so on. So yeah, let me know what you think. Throw it up there. And again, this is not a dig at anybody at all. I mean, absolutely nobody. And says, and if anybody thinks you can say, oh, well, oh, hang on, Ellen and Rusty Beauties must have been doing it wrong. I think, no, because I've done it the same way. So if he's wrong, I'm wrong. Do you know what I mean? We're all wrong. But it's just a different way of looking at it. So I just want to see, I mean, maybe I'm going to head down this route. Maybe I'm right, maybe I'm wrong. And again, that's the whole idea. It's just opinion. So throw up your opinion on it, just your opinion, what you think. And hey, maybe there's enough momentum. And again, if somebody wants to do it this way, that's a personal choice, right? It's a personal choice. At the end of the day, all these videos, no matter who does them, it's all about getting the best out of your engine as you can. It's all about helping each other in that way. So maybe this is helpful in one way. Maybe it just stirs the pot and it just makes you even more confused. Who knows? Anyway, thanks for watching and see you in the next video.